It's a pleasure to give a presentation about our work. I will introduce a cross-cutting research between read mapping and computer science, where the work is a combination of SunWay, TaihuLight, and read mapping. Our work is SWMapper, Scalable read mapper on SunWay TaihuLight. This is the outline of our paper. First of all, I will make a simple introduction about read mapping and SunWay TaihuLight supercomputer. Then I will talk about implementation, mainly about optimizing on SunWay. Next, I will show some results and evaluate our work. Finally, make a simple conclusion. Methods of read mapping typically fall in one of two categories, tree-based and camel-based. The tree-based approach is usually based on suffix tree array or FM index structure. This approach has the disadvantage that performance usually decreases as the length of reads and the number of mismatches increases. Mappers using the camel-based approach rely on a seed and extend strategy. This approach can produce many seeds and lead to long runtime for large-scale NGS datasets. A lot of efforts have been made to parallel read aligner on computer cluster. SLearner is the only camel-based mapper designed for the SunWay platform. SLearner data structure, however, is not able to fit into node local memory. We base our solution on a seed and extend strategy using a camel hash index as illustrated in figure. The reference is divided into substring of fixed length key, called camel or seed. The location of all these seeds are indexed into a hash table. Seeds are then extracted from each read and hash. Each hash value is used to probe and construct hash table of reference location. These locations are candidates for alignment between the read and the reference. Before alignments are actually calculated, and filtering strategies based on the pigeonhole principle can be used to discard large regions of reference. If we allow at most E errors, the pigeonhole lemma states that if a read is divided into at least E plus 1 line over seeds, then at least one of them occurs exactly in a match. In practice, a read is usually divided into more than E plus 1 seeds. Thus, we can just choose the E plus 1 seed with the fewest candidate location. Using this method, we can discuss many candidate locations. Now I will take a simple introduction. The process used for TaihuLight is the SW26010. TaihuLight is the SW26010. It is composed of 4 core groups, usually called CG. They connect via a network on chip. Each core group includes a management processing element called MPE, 64 computing processing element called CPE, and has 8 GB attached DDR3 shared memory. SW26010 SIMD instruction set features 256-bit wide vector type. Each CPE cluster is composed of 64 CPE codes which are arranged as 8 × 8 grid. Each CPE has a 64 kilobytes user-controlled discrete pad memory, but no data cache memory. The discrete pad memory is typically called the local device memory (LDM). Direct memory access needs to be used to efficiently transfer continuous block from main memory to LDM. We first determine whether there already exists a hash index and a compressed reference on file. If not, we need to initially build a hash index and compress the reference. The construct hash index and compressed reference are then written to the file system. If the hash index already exists, we read it from the file system. Double buffering is used to overlap CPU-side computation and MP-side data. We allocate two buffers for input NGS reads and for results. When there is no more date, we exit while loop and wait for last task to finish. In order to reduce memory usage, we use a succinct hash index. The traditional hash index stores the seed in a location, consuming a lot of memory. For example, for a human reference genome, it needs more than 12 gigabytes of memory. However, the main memory of each CG is only 8 gigabytes. So the traditional hash index does not be fed into the main memory of a single CG. The succinct hash index stores only one seed for every S consecutive seeds. The memory is S times less than traditional hash index. In the figure, the green seeds are stored and the gray seeds are discarded. A read is divided into long seed, which are further divided into short seed. We use short seed to find the possible match in the reference. In order to accelerate index construction, we have designed and implemented a distributed index construction method. First, the reference is divided into substrings of the same length according to the number of MPI processes. Second, each process calculates its own hash index as follows. For seeds of lesser k, we need 4 to the power of k buckets. We use the buckets to count each seed and calculate the number of each seed. Then we compute the prefix sums of the bucket arrays. The prefix sums are used as offsets for each seed. The locations of each seed are stored in the array according to the corresponding offset. After each process has calculated its own hash index, we merge them into a single hash index. We employ a dynamic task scheduling strategy to avoid imbalance of different CPEs. Figure shows our approach. FAW is an atomic addition operation provided by SunWay. It can add one atomically and return the old value. We use FAW to determine the rate to compute. First, we encode NGS rates into bit vectors. After that, we divide them into long seed and short seeds. We loaded the number of locations that each short seed matches in the reference from the main memory. We take the sum of the number of candidate locations for the associated short seed and the number of candidate locations for the long seed. We can choose the E plus 1 long seed with a fewest candidate location to compute the minimum number of candidate locations. We load the candidate locations from main memory and remove the duplicate locations. Then we get the sub-reference string from main memory. Then banded Mills algorithm is coded to calculate the edit distance between read and sub-reference. Finally, the results are compressed into gzip format and written to the file system. Different seeds may correspond to the same match position for a read in the reference. We cannot just store all candidate locations in LDM at the same time. We thus allocate a fixed size LDM buffer for each short seed and load only a part of candidate location into LDM. The location of each seed in the LDM are ordered. We set up a minimum heap data structure to sort seed position as shown in figure. This minimum heap contains only one position for each seed. Each element in this heap records the seed, the location, and the index of the location. When a location pops out, we will select the location corresponding to the next location in the seed and insert. When one location which needs to be inserted already exists in the heap, we will discard it. A new location is inserted if there is no duplication. We stop when there are no more locations. This method significantly reduces the time required for sorting. We can use long seed for further filtration. We take candidate position found by short seed of a long seed as the position that the long seed might match. The candidate positions are not necessarily the exact match position of long seed, but only the possible match positions. Thus, we further verify whether a long seed can match exactly at the location found by the short seed as follows. If an exact match cannot be made, the candidate position is discarded. Since long seeds are of less k plus s minus 1, and the less of short seed is k, we can exclude a large number of candidate positions. Thus, we store the s minus 1 basis before and after the short seed in the reference together with the location in the hash index to reduce time. We have two designed vectorized versions of banded Mills algorithm to accelerate the edit distance calculation between the read and substring of reference. For efficient vectorization, the data layout has to be transposed, so the data of multiple candidate positions can be accessed continuously. Actual implementation requires a number of bitwise logical operations. A reconfigurable ternary logical instruction log3x is provided by SunWay. Log3x can replace logical operation of 3 operands by a single reconfigurable ternary logical instruction. The left part is an example of log3x. First, the truth table D is calculated. Then the bits of ABC are combined to get the result from the corresponding location in D to get the final result stored in E. The right part is the implementation of vectorization of banded Mills algorithm. Now I will give a performance evaluation. We evaluate the performance on both simulated and real short datasets as shown in Table 1. The simulated rate D1 are generated from GRCH38 by the muscle simulator with default Illumina profile settings and the read length of 100. In addition, we use a real dataset R1 from NCBI SRA with read length 108. An entire machine is used for Razor S3, Bitmap 2, and Hobbies 3. In order to evaluate the accuracy of the mappers, we rely on the Rebema benchmark method. Table 2 shows the number of mapper reads and accuracy for Razor S3, Bitmap 2, Hobbies 3, SRN, and SWMapper for dataset D1 with an error threshold 4. We have tested the index construct time for GRCH38 for the hash index-based mappers Bitmap 2, Hobbies 3, and SWMapper. We only use the first chromosome from GRCH38 as the reference for measurement. Hobbit 3 supports parallel index construction and is executed in multi-thread mode, while Bitmap 2 can only use a single CPU thread for index construction. SWMapper and SNR are executed on a SunWay TaihuLight node. SWMapper uses 1 MPI process precision. Table 3 shows the results. We use 4 GRCH38 GNOME as a reference to measure the strong scalability of hashing index construction for SWMapper for up to 16 MPI process. And performance on real datasets, we use all real datasets R1 and map them against the first chromosome of GRCH38 reference. And SWMapper is the fast tool. In order to analyze improvements after each of our proposed optimization, we have executed SWMapper on 1CG using dataset D1 and GRCH38 as reference. Our initial naive implementation takes 264 seconds. We have evaluated two methods for implementing the long seed field. The first method loads the subreference into LDM for each position and compares the long seed between the read and the reference. The second method only loads the bases that are stored together with the location in the hash index. The second method achieves an improvement of 15%, while the first method only achieves an improvement of 12%. Our optimization achieves a great speed up of 11 compared to the naive implementation of a single CG. Table 5 shows the strong scaling result for SWMapper on TaihuLight using dataset R1 and the 4 human GNOME GRCH38 as a reference for up to 128 MPI process. Single process takes almost 2 hours to complete the task. Using 128 process, we achieve a speed up of 82. Performance decreases slightly as the number of processes increases due to load imbalance between different processes. All CGs work on parts of original input file containing the same number of reads. Next part is conclusion. We present the design, construction, and usage of a memory-efficient distributed succinct hash index structure for camels. Centered around this index structure, we propose a number of algorithmic optimization. We design and implement a vectorized version of Bandit Mills algorithm for pairwise alignment. Thank you.